Very warm welcome on the lecture. Actually, this is not 5, this is lecture 7 already from the 3D methods. That's about single particle analysis, the workflow, and how the procedures in single particle analysis works. What single particle analysis? Single particle analysis is nowadays the most well established method that we can use for determination of 3D structures of our model using cryo-electron microscopy. Although it's called single particle analysis, it's not using a single particle. It's using many more particles. So sometimes this single particle analysis for newcomers is a bit misleading. The single particle means that we are selecting single particles from our micrograph, and these particles are then used for the reconstruction process. The reconstruction process relies on the so-called projection theorem, or the application of the projection theorem, where we know that if we know all the possible views of or all the possible projections of a 3D object, we can assign the correct orientations of these views, then we can reconstruct the whole full 3D model. This is shown here on the side, that if we have a 3D object, we are irradiating it by electrons, we are getting a 2D projection of the image. The Fourier transform of this image is actually a single Fourier slice in a 3D space. So if we have a single, just this one, this single Fourier slice, this single Fourier slice is not enough to reconstruct our volume. We need to collect many more different views of our object, so that we will gradually fill our Fourier space not only in this direction, in other directions as well. We can fill it in diagonal directions and all the possible angles. The more angles we have, the more the Fourier space is complete, the more our model will be reliable, the more it will be isotropic, as well the resolution will be better. Concerning the specimen that we are usually using for single particle analysis, this method is the most suitable for analyzing of pure samples. In our case of cryo-electron microscopy, we are usually using biological samples, complexes, viruses, something that's small enough that could be electron transparent, yet big enough that it's visible on our micrographs. The sample is embedded in vitreous eyes. This we already learned about, that the preparation of the perfect sample, how to prepare it using the vitrification process. What we need to be aware about, that we need a thin enough ice to have a very little background from the vitreous ice. Yet it has to be thick enough so that our molecules are not affected by the air-water interface or the air vitrified water interface. Because on this interface, the molecules or the structure of the molecules is deteriorated and leads to lower resolution. What's ideal for the SPA to have a rigid molecule, and also ideal is that we have this molecule in all the possible random orientations in vitrified in the ice. The data acquisition strategy for single particle is pretty easy. Collect as much as you can. So what we need for it is, of course, a cryo-electron microscope. This is a must, of course. Nowadays, what we have on these cryo-electron microscopes, and is also a kind of must for single particle analysis, at least for high resolution, is a direct electron detector with fast readout. We will show why this is important and how we can utilize it. The more the readout of these electron detectors is higher, better, then faster we can acquire our micrographs, which are, of course, 2D projection images of a plane of a specimen. We need to be aware that the more we irradiate our sample, the more signal we get, Yet, the more we radiate the sample, the more radiation damage we introduce to our sample. So we need to find a balance for the amount of radiation that still gives us enough information, yet it is not destroying the high resolution information of our sample. Also, we need to find a nice balance between the pixel size, which defines actually the best achievable resolution in our during our reconstruction process, because of the Nyquist frequency that we learned already about in the previous lectures. But of course, it's not enough just to have a very small pixel size, because we are also limiting the view field that we can acquire using a single shot. So we need to find a proper balance, and we need to be aware of that because of the contrast transfer function, we need to acquire our dataset at varying defocus. Just for people who are not familiar how this process works, we are not acquiring the images one micrograph at different defoci. We are applying different defoci for different micrographs. So the first micrograph is, for example, acquired at -1 micron defocus, the second one at -1.2, -1.3 is the third one, so that every single micrograph has its own defocus that we will determine later, as I will show you. Now, why to acquire in movie mode? The movie mode is a very useful mode, and nowadays all the acquisitions for single particle are done in movie mode. This is because our cameras, their direct electron detectors, are able to acquire at a very fast frame rate. For example, the K2 detector can acquire at 400 frames per second. The K3 detector can acquire even at 1500 frames per second. This speed of the acquisition gives us how much electrons we can apply on our sample per second, because we want to see the individual counting effects on our camera. So if we have a fast camera, then the electrons can come to the camera surface fast, yet they will be recorded as single event electron events. If we have a slow camera, then we have to decrease our electron flux, and therefore all our acquisition times will be longer. Now we need to describe a little difference between the frames and fractions. Usually, or by definition, the frames are the internal speed of the camera. So the camera is always acquiring at this frame rate. For K2 it's 400 frames, for K3 it's 1500 frames per second. Yet we are not storing directly these frames. This is because we don't have fast enough storages for this to be able to store every single frame. But also in a single frame, we see only single electron events. That means that the single frame look like pixels like stars in the sky. There is nothing to see there. So what we are doing usually is we are summing several frames, and we are causing these fractions. They are calling fractions because actually what we are doing, we are fractionating the dose. So if we have a readout of the camera that has 400 frames, and we are grouping every 4 frames into one fraction, then actually in this one fraction we are storing information from an irradiation of electrons that happened during this one frame time. As well, because we have 400 frames, we will end up in 100 fractions. This is really what we are doing, because the dose that we have in every single fraction would be very small and would be unalienable in the later process. Therefore, we are choosing a fractionation that will give us around 1 electron per square angstrom on our specimen. That's usually around 40, 50 fractions from a 5-second acquisition on K2. Why these fractions are important? Because in these fractions we have state of our specimen frozen in that time point, and we have different time points. Therefore, we have a kind of moving movie. So we are storing movies of our acquisition. And this is where some confusion comes. Many times you can hear about movie frames, correcting movie frames, dose fractionating movie frames, or you can hear about movie fractions. We rarely use in normal conversation that our movie is fractionated. Therefore, many people are more used to movie frames, but these frames in the stored movie is actually fraction. So these should be properly named as movie fractions. Now, what we can do if we have movie fractions? Down here, we have a representation of a specimen with 3 dots, and these dots have a little bit different location on every single movie fraction. This location is defined by the drift of the microscope. This drift is usually caused by non-stable stage. There is no perfect stage, so there is always a little bit drift there. Also, it might be induced by heating, induced by the beam. We will cover the beam-induced movement with a different approach of alignment that you will see later. This drift movement is usually the largest movement of the specimen, and it's uniform, and it's usually directing to one direction. We can see that all our dots are moving toward one direction. Yet, what we know that this direction might vary slightly in between the frames, so it may change slightly the direction over the dose fractionation process. Now, how we can compensate for this drift-induced movement? This is one of the easiest way how to do it. We choose one of our fractions as the reference. We can choose the fraction number 1 as the reference, or fraction, let's say number 10, as we have 10 fractions here, as the reference, and then gradually aligning by cross correlation the other frames to this frame. And when we are satisfied with this alignment, we average it, and we have an aligned average micrograph, which should have a higher signal to noise ratio because the particles are aligned better on the whole micrograph. There is no drift in the micrograph, or the drift is corrected. The problem with this approach is that in every single fraction we have a small amount of signal. So we are aligning a very noisy fraction number 1 with a very noisy fraction number 2, or with a very noisy fraction number 3. So this cross correlation is not working extremely well. So there was developed a different approach. This different approach is an iterative process where we first take the sum of our fractions of all the 9 fractions except for the first one. This is the fraction that we are going to align on the sum of the other fractions. So now we will have this sum, which has a higher signal to noise ratio. It will be a nice clear image. And we are aligning a fraction that is noisy on it. Yet we will get better alignment cross correlation than on noisy versus noisy fractions. So we have aligned fraction number 1. And what we are going in the next step is that we are again going to sum all the fractions, including now the already aligned fraction number 1, but we are not summing in this sum the fraction number 2, which we will align in the next step. So now we are aligning fraction number 2 against the sum of all fractions with the already aligned fraction, the best aligned fraction number 1. And now we are aligning fraction number 2 on it. And we are proceeding with this to fraction number 3, where we are removing just fraction number 3, and we are using aligned fraction 2, fraction 1, and the rest of the unaligned fractions, We go up to our last fraction, which in this case is fraction number 10, and then we return to the beginning, where we have already somehow aligned all our fractions that should give us a better sum of fractions at the beginning of the process. And we are again aligning fraction number 1 against all these sums of fractions. Now, we can do this forever. So we need to define some borderline when the movement of the fractions or the error of the alignment reaches some value. Sometimes this is very tricky. Also, there is always a kind of fail-safe where we tell that don't do more than 5 iterations of this alignment. This way, we can align our fractions much better and much more precisely. Still, we are doing a whole image, whole frame or whole fraction alignment. So we are using the information from all the surface of the fraction that we are aligning. Now we will get toward the beam-induced movement that is not a drift. This is something that is caused by the beam, and is caused by one thing is that when the electron beam hits the surface of our sample or the irradiated area, it's starting to heat it. As well, beam-induced diminishment is going to happen there because the biological molecules are very sensitive to electron irradiation. This beam-induced movement is usually smaller than the drift, so yet it's better to correct for it, but this is a smaller movement, and it's more random-like. So not all the frame is moving in a certain direction with all the particles, but the particles are kind of moving in the random-like direction, yet this is not completely random-like, because it was shown that if we have our surface and we are irradiating it with electrons, the heating process will deform the surface in this kind of dome effect, so that our particles are starting to move upwards. This was proven by the fact that if you tilt your sample, then you can see that this upward movement in the direction of Z now becomes a lateral movement in the image plane. So because this dome effect is a kind of surface, there's a very nice way how to correct for it. First, what we do is we do a global alignment. Then we split our image in the so-called patches, and we are going to do patch alignment. So this micrograph on the image, what we have here on the slide, has 5 patches, 5 by 5 patches, and this largest direction of movement, what you can see here, is the total drift. This is the global alignment. The reason why this is colored is not because of the amount of drift that you can see there. This is because it shows the first and the last frame. So the first frame is the dark blue one, the last frame is the red one, and we see a nice continuous drift using the global alignment. Yet when we are doing patch-based alignment, we see that these patches of the already globally aligned frames or fractions are moving a little bit, and they are moving differently. There are sometimes larger movements and sometimes very minor movements. These minor movements are usually concentrated to the middle of the image because of this dome effect. And when we know how these patches are relatively moving in between each other or themselves, we can correct for this. We can do just a very easy shift of the patch, that this local region will be shifted in the direction where it should, where it's following the beam-induced motion. Yet this would lead to a kind of checkerboard effect, where on the borders we would see some discontinuities between these patches because these patches are moving independently. Instead of that, what we are doing is that we are fitting a second order surface on every single frame. So we have a second order surface For the patch movements for the fraction 1, we have a second order for surface fitted for the patch movement on the fraction 2 and up to patch 10. And then every single frame is deformed by this second order surface, fitted second order surface, and then we sum the corrected fractions. This gives us way more superior results, and it's a quite fast process. This local patch alignment works exactly the same as the global one, so it's an iterative process that ends until we define the limit. Now, we also need to consider that we don't have a perfect detector, and the detector often suffers or always suffers from so-called bad pixels. The bad pixels are pixels that are always on or always off, or they are always giving the same value independently whether their electron landed or did not land there. This is a problem because if these pixels are not varying in between the fractions, they are giving very strong correlation. So the software first needs to identify these pixels, which we are also giving a map of faulty pixels that we know from our detector. Yet it was shown that these two images, these two micrographs, were recorded one after each other, and they pointed out many pixels that were considered as defective pixels, and they are not sharing the same location on the panel B and the panel C. So there is also a software version how to detect faulty pixels. Now, another advantage of the dose fractionation is, or the fractionated movies is, that actually we can say what was the irradiation of the sample in a certain in the fraction that we acquired. Here was a very nice paper about it, how this dose weighting was invented. They did they recorded a full movie of 70 fractions, and then they do reconstruction from only the first 4th to 6th frame, from frames 25th to 27th, from frames 46 to 48, and frames 67 to 69. And what they know that in frames 4 to 6, the irradiation was only 3 to 4.6 electrons per square angstrom, whereas because of the continuous irradiation, by the end of the acquisition in the frames or the fractions 67 to 69, the irradiation of the sample, the total irradiation of the sample, was already 51 to 53 electrons per square angstrom of the specimen. What we can see that the low irradiation is not destroying the high resolution information. So in this reconstruction, we can see very nicely the side chains. The more irradiation is, the more radiation damage, and these side chains are getting more and more blurry until at a certain point you are not seeing the side chains at all, and only thing that you can distinguish is that here is a blob of helix. Now, we cannot acquire images only at the dose rate of 3.1 to 4.6 electrons, because these images would be unalignable. They also used the wall range for alignment of these molecules, and then they just used for reconstruction these defined frames. So what they found that if we can find that our signal to noise ratio is dependent not only the accumulated exposure, but it's also dependent on which resolution shell we are looking at, so at which resolution frequency. By the low frequencies, these 22 angstrom frequencies, are not extremely affected by the accumulated dose, because the signal to noise is very slightly decreasing. The high frequencies, these 4 angstrom frequencies, are affected very steeply. So when we are applying those 20 or 40, we are extremely decreasing our signal to noise ratio. So they measured all these effects. They found the critical exposure for the frequencies, and then the optimal exposure curve for the frequencies. And they defined a mathematical function where you will attenuate your amplitudes in the Fourier space for your exposed frame or fraction. So this n defines what was the exposure of the electrons for the current fraction, and the k defines the spatial frequency. And you can see that this is a function of k. So what you end up that for a low dose fractions, you are attenuating less the high frequency information than for the high dose fractions. So the fractions that receive the higher dose. And the final dose weighted image or the Fourier components, depending on the frequencies, so the low, high frequencies, will be weighted as the sum of all the fractions. So the ith fraction, now if we have 10 fractions, it's going from 1 to 10, where we are multiplying this attenuation factor with our original Fourier space component. So for the first fractions, we will let to pass, or we will attenuate less the high frequencies. For the last fractions, where the irradiation damage is the most and there was the most exposure, we are attenuating more the high frequencies. This is called dose weighting of the movies, and then we are summing it up and getting a sum of dose weighted micrographs. So frame alignment and dose weighting are the first steps of our processing. Often you get this already as a pre-processed data from the core facility. Both of these things use raw data. So they are using the movies, the fractionated movies, and both of these things are done in Fourier space. Why it is done in Fourier space? Because we already learned that in Fourier space we can do sub-pixel accuracy shifts, because what's a shift xy in the real space is actually a phase shift of the waves in the Fourier space, and we can very precisely control this phase shift in the Fourier space. There is one exception. The exception is deformation using the second order surface, which you cannot do in Fourier space. Also, this deformation can be combined with another real space deformation that's about the anisotropic magnification of the microscope, and the microscope has a different magnification in x and y axis. Nowadays, this value is very small, and we are correcting for this later in the processing. Because as we've seen, all this stuff is connected to the dose, to the fractionation of the movies. This is usually done by single software in a single step, single procedure, and it's outputting either aligned dose-weighted micrographs, or it can output also aligned non-dose weighted micrographs, which we will explain later why they might be useful for us. As well, because we work in the Fourier space, we can also export the power spectrum, which can be useful for further CTF estimation. Now, we already have our micrographs. Our micrographs, as we told, are collected the way that they are collected at different foci, because we want to avoid these zero nodes on the CTF contrast transfer function. But the problem is that when we are setting up the microscope and we are telling the microscope to set up a defocus of minus 1.2 microns, the microscope will set up a defocus of something very close to 1.2 microns. Yet this precision is not enough for high resolution CTF corrected refinements. Therefore, we need to mathematically approximate what the contrast transfer function of the image is. And this is quite easy. Well, mathematically easy. The implementation is a little bit harder for the software, but still this is considered to one of the easier steps. We know that the contrast transfer function is the function of spatial frequency. So the only variable for the contrast transfer function is the k. the spatial frequency, and we have several constants. We have a constant of defocus, we have a constant of wavelength, we have a constant of spherical aberration, and of course this natural constant pi. For CTF estimation, we will look for one of these constants. We will look for the constant defocus. We can do this very easily because we know that all our EM images that we've collected are convolved by the point spread function. Therefore, they are multiplied in the Fourier space by the contrast transfer function. And this contrast transfer function has an effect that we can see periodical missing information in the Fourier space where the contrast transfer function has a zero crossing. Therefore, we can fit over this our desired contrast transfer function, which will vary depending on defocus. Also, what we can do is estimate the astigmatism and the angle of astigmatism. But one thing, what's very important here is to note, because some people are confusing the CTF estimation, the estimation of the defocus of a single micrograph with CTF correction. So in this step, we are not doing any CTF correction. We are only estimating the defocus values, the astigmatism values of our micrographs. Here, just a little bit of refreshment what the 1D and the 2D CTF is. On the left side, we can see half micron defocus contrast transfer function when it oscillates from -1 to +1 in an oscillatory manner. And of course, we have these points where it crosses zero and information loss is happening because there is no contrast transferred at all. Now, if we take this 1D contrast transfer function and rotate it around in a 2D space, we will get a 2D contrast transfer function where we can see this nice periodicity of the waves, of the CTF waves. And these rings we also call so-called tone rings. So some people are saying that we are fitting tone rings, or whether tone rings are visible in the image. Just to let you know, the tone rings are visible only in the image only when there is some information in the image. So if there is some contrast transferred from the image to the detector. This is, for example, very easy to see when you are imaging just a pure vacuum, where there is nothing that would create a contrast. You don't get any tone rings. If you have a nice dense material, your tone rings are very visible. If you have a very noisy material, then your tone rings will be, of course, visible less. We can, of course, have a different defocus, a little bit higher defocus. If we have a higher defocus, then our oscillation is more dense. We can see it also on the 2D function. So we can vary with the defoci, and we can simulate contrast transfer functions that will differ in the periodicity. Now, also, I want to show you what the astigmatism is. The astigmatism is an image that has a different defocus in the x and the y axis. So it has a directional difference in defocus. Now, this has to be done in 2D because we are talking about xy directions. Here we have one direction. This image was simulated with a astigmatism that has a 45-degree angle against the x-axis, and in this direction we can see that we have some oscillation of the point spread function or the contrast transfer function, but in the perpendicular direction the oscillation is much faster, is more dense. We can see it on the green curve as well versus the red curve, or visually we can inspect it on our micrograph, or our Fourier transfer of the micrograph. This is simulated data. This is an extremely exaggerated astigmatism. Yet here we can nicely show what it does in the Fourier space, and that we can describe this astigmatism as an astigmatism that has a certain angle against the x-axis. As well, we can define it either like a smaller defocus and a larger defocus. So what's the defocus in the in the smallest defocus, and what's the direction in the biggest defocus? These things are always perpendicular to each other, or we can define it as a mean defocus of these two plus the delta, that's plus minus over the mean. Some software prefers to use one, the other software prefers to use the other one. The angle of defocus always defines in which direction this ellipsoidal deformation of the tone rings is happening. Now, how we are doing the CTF estimation? We are taking our micrograph that we already aligned using the motion correction and doing a fast Fourier transform. Now you can see that in this fast Fourier transform, we don't see extreme much of information, yet we can see a little bit of the tone rings. A thing that is rarely mentioned, that this fast Fourier transform has to undergo a background removal process, which is done in the Fourier space. The reason for that is that if we would plot our CTF function without this correction, the CTF function would have this direction, so it would gradually decrease. Whereas if we do this background removal, we will get a nice flat representation and oscillation of the contrast transfer function over this flat curve. Then we see that this image is very noisy. What we will do is that we will take a rotational average of the 2D spectrum. The rotational average is in the polar coordinates, taking one profile of our 2D Fourier spectrum. We see that in this profile we don't really see the tone rings. They are there, but they are very noisy. So we will take another profile, and we will make a rotational average of all the 1D profiles. And what we will end up, this is just a rotational representation of the rotational average, is that we really see from our Fourier transform the tone rings. Nice, smooth, fittable. The problem is first approximated in 1D, so we are only doing a section of this. We are doing a 1D approximation of the defocus. However, in 1D, we cannot estimate the astigmatism and angle of astigmatism. Therefore, we are continuing with the 2D refinement of the firstly estimated 1D defocus. And what we will get a theoretical curve, a theoretical contrast transfer function that we can compare here on the edge, how well it fits our data. Also, we can see some of the radial averages of the 1D plots, where we see the orange curve is the measured defocus, and the green curve is the fitted defocus. Now, vice versa. It is vice versa. Now, also what we can determine is how well these curves correlate together. And at a certain point, we will see that the correlation drops. Sometimes this drop in the correlation at the high frequencies is stated as the resolution of the micrograph. This is, however, something that should be taken with care, because this is just an arbitrary chosen resolution, which depends also on the amount of information, amount of signal that is present on the micrograph. So our very high frequencies might be extremely attenuated if there are not enough particles, for example, on the micrograph. Therefore, if you are checking your micrographs and seeing that this micrograph is going only to 5 angstrom resolution according to CTF estimation, and the other one to 3 angstrom, that does not necessarily mean that the 5 angstrom micrograph particles are worse than the particles from 3 angstrom determined micrograph. Now, If we go back to our motion correction, we told about that we have an ability to export not only the dose-weighted but also the non-dose-weighted micrographs. And the reason for that is that on non-dose-weighted micrographs, we have a very nice representation of all the frequencies that we have in our uh, data, also the high frequencies. These high frequencies are not down-weighted. So you can see also the high frequency information there. Yet, or this might be, of course, burned information. It might come from the carbon edge of your support film, but it helps for the estimation of the CTF. Whereas in the dose-weighted ones, the high frequencies, of course, are dumped down in the sum. Therefore, these micrographs are less suitable for CTF estimation. Yet, it's doable also on these micrographs to do the CTF estimation. And then the problem of slightly incorrect CTF fitting might be corrected in later steps using CTF refinement process. Well, I want to recommend to all the people who are using who are estimating CTF by any of the tools is to check. Well, it will be hard to check all the thousands of micrographs, but first just check your micrographs if the fit of the CTF is good. On the left, we can see a very nice fit of the measured and the theoretical CTF curve, whereas on the right, we can see that this micrograph has very weak tone rings. Maybe the micrograph is bad at all. There are no particles. This might happen. But if you see that all your CTF fits are this bad, then something happened during the acquisition process. And all your micrographs, maybe the motion correction has to be checked and inspected. Also, what's happening sometimes that you have very nicely visible tone rings on the measured data, and you have a very misfitted tone rings on the simulated data. This usually is because you've chosen the search range for your CTF estimation in a wrong range. As we told, we are varying with the defoci. We usually set up a lower bound and the upper bound of the focus because we don't expect that we are going from 0 till 100,000 microns of the focus. Rather, we know that our data was acquired from the focus -1 to the focus -3. Sometimes it happens that there's a larger offset in the microscope, and then you will have even micrographs with the focus of -0.7, and they would be out of our range. Therefore, if you see images like this, when you've done your CTF estimation, check the search range and rerun the CTF estimation process. And the last thing, beware of the correct microscope parameters. As we told, not only the focus is the constant that affects the contrast transfer function, but it's also the wavelength of the electrons, which is connected by the de Broglie equation to the acceleration voltage. And the interesting thing, what we will find out, that you can fit CTF very well with the wrong settings of the microscope. This data was collected on 200 kilowatt microscope, yet if you forget that this was not collected on Cryos, rather on Artica, and you run your CTF estimation using parameters set to 300 kilowatt, you will get nice fittings, but the defocus values will be greatly different. So you see here the defocus values are -2 microns, where here it's almost -2.5 micron. So beware of this correct microscope parameters. For all microscopes, the CS value is the same, yet the acceleration voltage depends where you are collecting on Cryos or Artica. Now we have perfect micrographs. We have estimated CTF. It's time to pick our particles. The picking of the particles is essentially the selection of the areas of interest. We can do manual picking. We call these hand-selected particles. They should be of the best quality, although this is not always the true. The good thing about manual picking is that you get an overview about your data set. Sometimes you will find very interesting things. Sometimes also you see, for example, that there was some misalignment of the microscope because half of the micrographs is collected on the carbon instead of the whole. So sometimes this manual picking or inspection of the micrographs can give you valuable input or output. Then you have automated selection of the particles. This can be done by auto-picking defined by some blob estimation defined by the particle diameter, or you can auto-pick by a template that you already know, or the most modern methods and the most used methods nowadays, I would say, are the convolutional neural networks applied on your data. Beware that all of the manual or all of the particle selection suffers from false positives, but don't try to be perfect. There is no perfect picking method, and later in the later stages of the process, we will get rid of the false positive and the junk particles. Manual picking, as we told, sometimes the best particles, yet these particles are rarely well-centered because there are always differences. If you pick that here is one of my particle, I can barely see this particle, maybe the center is here. You will get quite large errors in the centering of the particles. There is always a human error if the human see or does not see the particles well. Usually, if you don't see the particles, they are not there, yet there are some aids that you can do. Something like low-pass filtering that will greatly enhance your contrast. We already talked about this when we were talking about Fourier transform. We'll also talk about this later in this on this lecture. So here we can definitely see better all the particles that we maybe want to select, and we can define it better. There are also other approaches like kind of noise-to-noise or denoising, which is also based on convolutional neural network and works pretty well for small particles. Although manual picking is not used anymore as the main picking method, it serves as picking for the templates for the automatic picking methods. Now, as I told, the automatic ones, these are either size-based methods. One of the main used method here is the Laplacian of Gaussian. It's a blob detection algorithm where you define the so-called kernel size, which is proportional to the particle size. You run this filter on your image, and instead of seeing particles, you will see brighter or darker peaks, and then you can just select these peaks, feed all the selected particles in the 2D classification, where you may get nice 2D classes that are suitable for further template-based particle selection. Template-based, of course, needs a suitable template. This is done either by selecting some 2D class averages. Here the important part is that you need to select most of the orientations in the plane that you have of your particle, because the search will only do in-plane rotation of the 2D class average and looking for its correct position in the micrograph. So you have to include all the top side, diagonal and other views of your particle. And if you don't have them, you need to better find them, because otherwise you will suffer of missing information. Also, what you can do if you have a structure that is very similar to an already known structure, for example, like a ribosome or virus, then you can generate 2D projections at the sampling rate, a certain sampling rate from a 3D structure, and use this as a template for the template matching or the particle selection. The selection is based either on correlation between these two or the maximum likelihood version. We will speak about maximum likelihood method a little bit later today. The problem here is usually that the output needs to be properly thresholded, because this method gives a lot of false positive outputs. Usually on the edges there are false edges of the carbon, there are false positives. It's quite computational intensive because you need to run a correlation in all the possible orientations of all the templates that you are using for the matching. The last thing that nowadays are used, and these things are really heavily used because they are working very well, is trained convolutional network. Here you have a small training data set of tens to 100 micrographs where you try to select, uh, usually manually, all the particles in all orientations that you are interested in. Then you are training a convolutional neural network and all its hidden layers, and you end up with a trained model. This training process, in this case, takes the most of the time, whereas the next step, the particle picking, where you are predicting the particle positions by the trained convolutional neural network that we trained in the first step, is quite fast. They stated in their paper that it's up to 5 microns per second. So the step that here takes the most of the time is first manual picking your particles and then training of the neural network. The good thing is that they already pre-trained the neural network or several different data sets. So sometimes this general model that is available from the authors can be used as an out-of-the-box solution and may work for your data set. Also, one advantage is that you can specifically train your neural network. Here is shown that if the neural network was trained for the top and the side views of this keyhole limpet hemocyanin, then it picks all these views. Whereas if you just take on side views as the for the training model, it will predict only the position of the side views of the complex in the micrograph. Now we have picked our particles. The particle picking itself does not mean that these particles are already boxed out. This is because the particle picking, in fact, just defines the particle centers, the particle coordinates inside the image. Or in case of the template-based, it can also store the angle of rotation of the template, how it correlated the most at a certain point. Yet we need to extract our particles. And here is a thing that many of the people that are starting with cryo-electron microscopy is not using properly, is setting the box size. The box size is of course affected by the particle. The box size is the area of the micrograph that we are selecting as a single particle. So the bigger the particle we have, the bigger box of course we will need to have to include all the particles inside the box. Yet we cannot choose a very large box because then the computation will be very slow. Also, we cannot choose a very snug box that will closely enclose the particle with a very tight tolerance because it is not suitable for the next process of background noise estimation, as well for the CTF correction, where need to relocalize the localized signal caused by the contrast transfer function or the pointer function. So the rule of thumb is choosing 1.3 to 2 times bigger box than your molecule is. If your molecule is small, then choose a 2 times bigger box, like an apoferritin. If you have a very large molecule or a very large complex, like for example a virus, you can go down to 1.5 or 1.3 because the signal delocalization depends on the edge of this, and it's defined by the distance from the edge of your object, not by the size of the object. So the signal delocalization for the small object is delocalized to the exactly same distance as from the large object. On the next slides, we will show how and which box sizes are proper. Also, we need to take care about inverting contrast. So far, we worked with micrographs that had black black particles on white background or bright background, dark images or dark particles on bright background. Now we need to invert this contrast to white particles on dark background. Be aware if at some step before this particle extraction you inverted the contrast of your micrographs to preserve that you need to have white particles or dark background, because all the uh, refinement classification software is optimized to maximize the signal, not to minimize it. So it will not work with dark particles. We also need to normalize our particles. We will talk about it a little bit later. And optionally, we can scale or resample the particles to speed up the computational process. Now, concerning box size. Box size must be an even number. This is that I think all of the crime software insist on, that your box size has to be an even number no matter what, and it will run in error if it is not. But there are tons of even numbers that we can choose from, and I will show you why some of these numbers are more and some of them are less appropriate for the selection. Let's take some nice round number of 128 and do some prime factorization. Prime factorization is decomposition of this number into a multiplication of individual prime numbers. So we can decompose this as a 2 times 64, where 2 is already a prime number, the 64 is not. 64 we can decompose to 2 times 32, and that 32 we can decompose to 2 times 16, and we always see that we are getting more and more prime numbers, as here we see that we can decompose that 128 into 7 prime numbers, 1, 2, 3, 4, 5, 6, 7, and all of these are 2. So 2 times 2 times 2 times 2 times 2 times 2 times 2 will give us 128, or 2 to the power of 7 equals to 128. This is a very nice number because it decomposes to the smallest available even pair number, even prime number. Now, if we take a different number, a little bit smaller box size, we see that we can decompose this 100 into 2 times 50, 2 times 25, and 25 we can decompose to 5 times 5. We see that we have two very small and two a little bit bigger prime numbers, yet the 100 would perfectly serve as a good box size. However, if we go slightly bigger, yet still smaller than 128, to 106, we can decompose this into prime numbers 2 and 53. And 53 is a pretty large prime number for our purposes. Why it is so? Because not all even numbers perform equally well for computation. So for the reconstruction process or all the data processing process, this box size should work. It should not introduce any artifacts. What will happen is that this box size will perform time-wisely worse during the computation than these two other box sizes. So the fast Fourier transform algorithm that is used for every SPA software likes to have the biggest prime factor of the number, of the box size number, as small as possible. Now, of course, we think about our data set and we want to find out, okay, 864 will be good. We can decompose it into these prime numbers, and finding out that, okay, this is composed from 2s and 3s, this might be good. Well, there are people that are already worked on this and also simulated what's the difference in between larger and smaller box sizes with a good prime number decomposition and a bad one. So here we can see our nice box size of 128 that has a processing time of around 5 minutes. And here we have the 106 that we talked about, that we have a smaller box, which should indicate that our data processing should proceed faster and it should take less computational time, yet it takes more than 5 minutes. The higher with box size we are going, the more this difference will be notable. So here you can see that for some books around 170 something, we have 22 minutes, whereas a little bit bigger box size will give us half of the time of the processing. Also, you can notice that this curve is kind of not varying in this region of small boxes. This is because the small boxes you can always decompose into prime numbers that have a very small factors. Now, not to need this large image and to find which box size is which one, you can go to some program or a web page where they already tested which box sizes should be good for the fast Fourier transform. And you can see that not only these 2 to the power of some factors are the good box sizes, but there are many other options that you can choose in between to have a decent ratio between the largest of the box and the processing time. We talked about the signal delocalization, why we need a larger box than the particle size. So if we would have a particle size, this is the size of our particle, and this would be our box size, then our image, when it's convolved with the contrast transfer function, is delocalizing the information from this image to the surrounding. And if our box would be this tight, then we would discard all this information around our box and would not be able to so-called relocalize it using the CTF correction. When we are using a larger box, as in this case, we have a box of this whole image, then using the CTF correction, we can relocalize a half of the signal. This will be discussed in the more advanced methods, back into this image using the CTF correction. But for that, we need to have the signal in the box. If the box is too tight, then we cannot relocate this signal. And another thing is there's an optional thing of binning. Binning is a kind of scaling or in real space or Fourier space. In real space, it's very easily describable, like replacing a value of 2 by 2 pixels into a single pixel. So if we have a binning of 2, then we are taking 2 by 2 pixels, averaging them, and putting it into a single pixel. What this will make is that we will not 2 times decrease the amount of pixels, we will 4 times decrease the amount of pixels, because we will decrease the amount of pixels 2 times in the x direction and 2 times in the y direction. If we bin it 4 times, then we take 4 by 4 pixels, average them, and put it into a single pixel, and this will 16 times decrease our data, the amount of data that we are using for the process. The problem with the real space binning is that it needs integer values, whole numbers. We can do binning also in Fourier space. We already learned about this. I will show it on the next slide. Meanwhile, the properties of scaled or binned images is that we are decreasing the pixel count. Also, we are decreasing the possible achievable resolution because we are decreasing the Nyquist frequency, because by decreasing the amount of pixels, we are increasing the pixel size. So we started, for example, on the left with the pixel size 1, and then we got to pixel size 2 by binning our data 2 times. So this effectively kind of low pass filter our data, as well as will limit us in some stages where we won't achieve, we cannot achieve the maximum resolution from our data set. Sometimes it's desirable to bin your data because you will speed up your processing, and you still know that for your dataset you are not able to achieve the Nyquist frequency, so therefore the bin data is totally suitable for your process. The Fourier space binning is a kind of Fourier space cropping, where what you do, you take your image and then crop it in the Fourier space. You will have a smaller crop out from your Fourier space, but if you do an inverse transform of it, you will get a downscaled image. And here you can nicely see that the binning itself is a low pass filtering, because what we are doing, we are discarding all these high frequency data so that they are not anymore present in our downscaled image. They cannot be present there because they were cropped out. So we are in fact low pass filtering our image. Another thing that is largely unknown that's done during the process of the box extraction, when you already defined how big your box will be and going to extract your data from the micrographs, there are contrast differences between particles. There are contrast differences because of the thickness of the ice. Some particles you are picking on thick ice, some particles you are picking on thin ice. Sometimes there's even a gradient of ice over your particle. So what you need to do is to normalize these images, because for cross-correlation refinement, this is not a problem. If you do a refinement that's engaging cross-correlation methods, cross-correlation is invariant to normalization of the particles. It will work the same as it would work with normalized particles. However, the maximum likelihood techniques are extremely sensitive to proper normalization, and nowadays we are almost exclusively using maximum likelihood techniques for reconstruction of our particles. These maximum likelihood techniques considers that all the powers of the noise and all the powers of the signal are equal. For normalization, we have different approaches how we can do it. We can normalize the whole image. The normalization of the whole image is essentially done by subtracting the image average from the image pixel values and divided by the standard deviation of the image. This will give us an average value of 0 of the process of the normalized image and the standard deviation of 1. We can also, which is done more frequently, normalize only the background, so the signal that is not affected. We choose the surrounding of the particle, that's why we need a larger box for the normalization, and we do the same as above. Or we can fit a planar functional rate. Also, we can use some filters like high-pass filters, but this should be, again, avoided in maximum likelihood approaches because it creates some artifacts in the Fourier space. Now, this is just a showcase of image normalization, where you can see in the original particle image that there's a gradient of ice, and if you are normalizing it with a plane, then you will have a nice evenly normalized image, or you have some extremes of from some contamination in your images, and because they are considered as background, they are not that visible in the normalized image. Now we are ready to align our particles. And to align our particles, first we need to describe some approaches that we are doing in the real space or Fourier space. So any rotation in the 3D space can be described by 3 Euler angles. Euler angles are 3 angles that are describing any rotation of an image, of a particle, of an object in the 3D space. There are many conventions of Euler angles, and we will use for explanation of this convention ZYZ. But there is also convention ZXZ. There is convention ZYX. And you will see that these conventions only differs how these rotations are proceeded in sequence. So for the ZYZ Euler angle convention, if we want to have the final rotation of our image or of our particles, the first rotation Euler angle phi, or it's also called as the angle rot, the rot angle, is the rotation around the axis z. That's why it is ZYZ. So we have a z-axis. Here's the z-axis. Here the circle represents our image, and we are doing a rotation by phi angle. We will get our y-axis to the axis y prime, and this new y-axis is then used to rotate the whole plane around this y-axis, the newly created y-axis, by uh, by the angle theta. So what will happen is that we have our y-axis here, and we are rotating all this plane around the newly created y-axis from the previous step, and we've got this rotated plane. And this rotated plane has its newly created x prime axis and the z prime axis. Because we were rotating around the y-axis, y prime axis, this was not affected at all. It was the same in the previous case where we only transformed the y to y prime, x to x prime, but because we were rotating around the z-axis, the z was unaffected. Now the y was unaffected, all the rest axes were affected. And now we are performing the third rotation. The third rotation is called psi rotation, and this is rotated along the newly created z-axis. So what we will do on our rotated plane, we are rotate by a psi angle on the new using the newly created z-axis. And any rotation in the 3D space you can describe by the combination of these three angles, the phi, theta, psi. However, many softwares have their own nomenclature for this. One is called angle rod, the other one is called angle tilt, and the third one is called angle psi, which is actually the psi angle. The reason for that is that if you take a look, the first angle shows the rotation of the whole plane, the second angle shows the tilt of the plane, and the third one is again an in-plane rotation on the tilted plane. Now to make it a little bit more interesting, for in-plane rotations, that means that we are not doing a 3D rotation, just a 2D rotation, we keep the psi, we keep the phi and the theta angle 0. That means that there will be no rotations from y to y prime, and there will be no rotation on this new y prime over this new y prime axis, so we will stay in plane. And this plane will be exactly the same as this one here, so the psi angle will do our in-plane rotation. So when we are doing in-plane rotations, we are rotating using the psi angle. Now, again, some things looks easy, some things are not that easy. Making a uniform angular sampling in 2 dimensions is quite easy. So we take our psi angle and we will rotate it in the range of 0 to 2 pi radians by a given sampling rate. So the sampling rate will be our step. So we have our image in a 0 rotation, this nice penguin on the right, and then we want to rotate our penguin by 30 degrees, so we make a 30-degree rotation. And if we want to make a uniform angular sampling, that means that we want to rotate our penguin by every 30 degree. This we can go all over the circle, and we will see that this was pretty easy. We are just incrementing by 30 degrees the rotation angle, and we get back to 0. So we have all the orientations at the sampling rate 30 in the range of 0 to 2 pi radians or 0 to 360 degrees. So in 2D, this is not a problem. However, in 3D, uniform angular sampling is a little bit bigger problem. The reason for that is that if we combine all the steps of these 30-degree steps with the phi and the theta angle, then we get something like this on the globe. And what we see that the points here and here are in a certain distance, whereas here they are getting closer. Oops, sorry. Here they are getting closer, and towards the poles, the views are getting overrepresented. So right at the very pole, in this exactly the same point, you have multiple samples, multiple angular samples. So this is not an even distribution. This is clustered towards the poles. There are many mathematical ways how to solve this problem. One of these ways how to solve it is called hill peaks. And helipix was originally invented for astronomical measurements. They tried to evenly sample the sky for the telescopes, and they invented a way how to easily divide the hemisphere into equal distant pieces. So what they are doing is that the sphere is hierarchically tessellated into curvilinear quadrilaterals. What is curvilinear quadrilateral? Quadrilateral is, for example, a square. So you have some kind of square, and the curvilinear means that this square is projected on our spherical surface. And then also there's a word tessellation. Tessellation is in fact filling a space, a surface with a tiling of regular polygons. So you choose a polygon and you are fitting these polygons next to each other so that they completely covering a surface. Here you can see tessellation using hexagons, using squares or triangles, but these can be even more complicated polygons. For example, if you walk on the sidewalk, you can see this nice mosaic where actually from the same structure you are covering the whole surface. So this is also kind of tessellation. And in our case, we are tessellating, covering the whole surface of our sphere using these squares on the surface. The good thing is that the distance between all these points is equal. So the Euler angles, then the equal sampling is represented by a vector that is pointing towards this dot. If we want to increase the sampling rate, what we are doing is that we will divide this surface into 4 equal pieces, what you can see here. And then again, the dots will represent the uniform sampling towards which the vector of the phi and theta angle will point to. And this you can divide to finer and finer samplings until desired sampling rate is achieved. Now, this is just to show you how differently it looks when we have this uniform angular sampling in 3D. So I've chosen here an angular step of sampling of the wall C1 space, where you can see from the file where these samplings are stored that we have a pairs of angle rot, this is the phi, angle tilt is the theta angle. These are the combinations, and we have 49 combinations of these angle pairs. Plus, we have this in-plane rotation using the psi angle, which has this classic 30-degree step. Before we continue for the classification and refinement process, this will be a very, very brief introduction to maximum likelihood methods, why the maximum likelihood methods works a little bit differently than the correlation methods. So in maximum likelihood method, the reconstruction problem is formulated as the finding of the model that has the higher probability of being the correct one in light of the observed data. So in the maximum likelihood reconstructions refinements, we are actually looking for a model that will describe our data the best. Here we can see a measured image, noisy image of a penguin. And here we have a nice penguin as a model, and we are looking for the correct orientation of this model that will represent the most our measured data. So we can, because this is a 2D image and we are going to do just some 2D alignment, we can rotate by some angular sampling rate our penguin and measure the probability. This is the probability that shows us how well this model describes this measured data. And we see that if we are rotated by 90 degrees, that's not very probable that this is the correct orientation of our model. And when we are rotating our penguin towards the right orientation, the probability rises, and then the probability has some maximum, and then again decreases. And then there is again some probability when we have, for example, this 180 degrees rotated correct orientation, that it has also some higher probability of being considered as the correct model. And this is very important here, that we are not selecting just a single orientation of our model that is the correct. We are selecting all the probabilities that which orientation of our penguin is how probable representing the correct orientation of the penguin. Of course, in reality, this is not the truth, because the truth is that if we have a particle in our data set, it has only one orientation. This penguin also has only one orientation, one correct orientation, and there is no other correct orientation. Yet, because of the noisiness of our measured data, it's a lot more feasible to do, or even more correct to do, integration over all the probabilities of these orientations of the penguin and considered as be the right orientation with different weights. So the most probably orientation will get the highest weight, the least probable orientation will get the lowest weight, and in between orientations will get high but still lower weights than the highest one. So using this, we can take, for example, our measured data and compared our measured data rotation against our reference. Here we have a reference of the standing penguin, and these images are representing how probable is that single rotation of the penguin with the reference. If it's very dark, it's very highly probable. It's very faint, it's not too probable that that's the correct orientation. And what we will do when we are generating our next, the A+1 reference, is that first we find the functions or all the orientations and the probabilities of these orientations for all our particles, and then we sum our orientations with different weights on that are scaled by the probability. So this image will be weighted very down weighted, whereas this image will be very high weighted. This one will be somewhere in middle, but none of these images will be discarded. They will be used for the final average of our A+1 reference. Also, in this maximum likelihood, there's a threshold where we are considering what's significant and what's not significant. So this is a nice statistical method that actually works with the noise level of your image. And this is also the reason why we need to have larger box size. Now, we learned almost everything we need to know for the 2D classification. The 2D classification is computationally quite easy process because it's performed only in 2 dimensions. It has only one rotational angle, that's the in-plane angle, the psi angle, and there are 2 shifts, x and y shifts. And what you are doing, you are trying to classify your selected particles into k classes. That's the number of classes. Nowadays, this is a reference-free method, in contrast with 3D classification or 3D refinement, because they found that we can generate the references out from the data very easily. We just randomly distribute all our particles into k classes with random orientations. We make an initial average of them, and then we are classifying against these classes our particles. It is an iterative method. First, we are classifying at low resolution, and with every next iteration, with some signal to noise ratio, we are trying to estimate if the resolution improved, and if the resolution improved, then we are including more and more high frequencies. To even more speed up this process, if we are working in the maximum likelihood based algorithms, we can even a little bit solve this thing with the regularization factor, whereby the regularization factor we can restrict or allow how much of the high frequencies should be included during the classification process. This 2D classification can be easily implemented in real space, like you are using the images of the penguin and rotating these images in real space and correlating next to each other, which actually works, of course, also for the maximum likelihood in real space. But nowadays, it's almost exclusively done in Fourier space because it was found that in Fourier space it works even better, mainly for the maximum likelihood approach. So what we are doing the 2D classification, we are looking for the best fit into a certain class when applying a certain shift and rotation on the particle. For this, we need to try all the shifts and all the rotations of the particles, as well as all the shifts and rotations has to try the best fit into the classes. Good to know about 2D classification that this process is mainly used for removing junk particles. So as I told, we have many false positive particles, maybe many damaged particles. 2D classification is rarely used for high resolution stuff. So for 2D classification, it's very beneficial to use bin particles to speed up the process. Okay, I think this I already discussed on the previous slide. What's interesting here is that the parameters for 2D classification is essentially the number of classes. We can define a rotational sampling rate, so how this full circle in 2D space will be angularly sampled. As well, we can define how far we can move with our images of the particles. That's the translational range. And in the maximum likelihood method, we have also this regularization factor that I told about. Now, this is just a showcase how 2D classification works. This is the iteration number 0. Here we have nice blobs. If you take a look on this image, it looks like all the blobs are exactly the same. But they were actually generated by randomly distributing all our measured data into random orientation and average together. To show you that these particles are not the same, I made a subtraction of the class average 2 from the class average 1, and I get this hazy image. But what the interesting part now is that if I subtract class number 3 from class number 1, I will get a different image. That means that there are differences in between these classes. So if we go further to for class 4, class 5, we see that all these differences looks different. So these classes are not the same. They are slight variances in between these classes. And what we are now going to do is we are taking our noisy particle and try to find the correct class and try to align it into the most correct class. So we will try it with one class, another class. We will try to rotate the particle into a different class. In fact, we will try all the orientations and all the shifts into all the classes for all the particles. And where they fit the best, then we leave the particle in that class. We apply the best orientation of this particle image and average sum together with the other particles from the same class, and we will get a 2D class average. So sometimes it's not correctly said that we are using 2D classes. We are not using 2D classes. For example, as our references, we are using 2D class averages because these class averages are the averages of all the particles in a certain orientation that are stored in that class. Now, if we do 5 iterations of this, so we have better and better class averages, and we can sort our particles better and better. We can see that we have many junk particles here. We have some nice differently oriented particles. Now the problem starts here for the maximum likelihood methods, that after a while the maximum likelihood method starts not only to classify depending on how beautiful and nice our particles are, but it starts, like for example here at iteration 10, to empty the classes and moving all the particles into the best classes. This is because in the best class we have a very high signal, very low noise, and actually this classification is starting to be driven by lack of the noise in these class averages. And this is why, for example, in Reline, when you are doing it with the maximum likelihood method, the 2D classification, then you need to monitor not only the last iteration that you define that you want to see that, but all the in-between iterations, because you need to find a balance where you still have your junk particles in junk classes and the nice particles more or less in the nice classes, whereas not only you have nice particles and the junk particles are disappearing. For example, in iteration number 15, you have only these classes, and trust me that in these first 3 classes, we have not only beautiful and nice particles, but there are a lot of junk particles. Solution for this is taking the 2D classification from an earlier iteration, discarding the bad particles, and the good particles you can feed to another round of 2D classification process. Now, a 2D classification, as I told, was a very easy process because we are optimizing a very easy problem in a two-dimensional space where we are limited only by one search angle and two translational components. In 3D, the problem is a little bit worse because this is not solvable just by a random initialization of our data set, of the reference of the prior. We need to have some initial model. And initial model, in fact, is the biggest problem for the single particle analysis, because in single particle analysis, there is always a danger of model bias. What the model bias is? The model bias is that if you have a nice initial model with many high resolution features, then because the noise in your particles is also occupying the high frequencies, the high resolutions, you are able to align your particles independently on the low resolution content to fit the best the high resolutions. And this is called overfitting, and it leads to something that if you put in something as an initial model, you will likely get something very similar to this initial model when you align your particles, and it's misleading that that's the true structure. How to solve this problem? Nowadays, the solution for it is to have a low pass filter your initial model, so that you are not at the beginning of the refinement process, you are not including any high resolution information. You are just giving a generous low pass filtered blobby 3D model that should somehow resemble your structure. Now, to generate an initial model is not that easy. You can use for initial model geometrical models as a sphere. So you know that your particles kind of resemble spheres. Then you can start by a geometrical model of sphere, or if it's elongated, you can try a cylinder for some fibers. Or what you can also do is use a structure as an initial model of a known structure. This is, for example, case of ribosomes. The structures of ribosomes and the shape of the ribosome is very well known, and you are, for example, doing data acquisition of a ribosome with some inhibitor, and you know that the overall shape of the ribosome will be the same. The difference will be only in the binding of the inhibitor. That's a very high-res data, high-resolution feature. That means that you can take a general ribosome map, low pass filter it to, for example, 40 angstrom, where you can barely see just the overall shape of the large and the small subunit, but it serves very well as an initial model for the refinement process or the classification processes. That's the same, for example, for the icosahedral viruses and other known models. Then, of course, you can generate your de novo model from your experimental data. This can be done by a very known command line method that Dr. Novacek already told you about in one of his presentations. We can also do subtomogram averaging, where we don't have only a two-dimensional data, but we have a three-dimensional data with some missing information. Still, it's easier to align as an unknown 3D problem than just from 2D data. This is, of course, a problem that we need to collect a new set of data and collecting tomograms and processing tomograms. We can use the random conical tilt. This also needs some collection of new data using the tilted stage. And then there is a quite new method of stochastic gradient descent optimization of the problem. And this, I would say, was one of the breakthroughs for the initial model generation, because usually these common line methods and random conical tilts were not giving very satisfying results. The problem with the good and bad initial model is that if you do a random initialization, that means that you take your particles, assign them random angles, making a back projection of it, and getting some 3D blob, it often leads to future alignments that gives you a nonsense structure. Whereas if you initialize your reconstruction or refinement process with a nice model, which is close to the truth, yet it's missing the high resolution information, as you can see here, then the refinement process catches well and converges. So here it is going to not local minima, but the maximum of the probability of the correct model. Then it goes to the correct maximum. The problem here is that if we go to this local correct maxima or local maxima, we see that if we move to the left or to the right, we are going downhill. So it seems that the probability that the correct model is outside this area is low, yet we need to overcome this valley to get even higher. To overcome this problem, there's stochastic gradient descent model generations, and this is also starts with arbitrary random initialization of a 3D model, but there's a process where we are only aligning always a subset, a small subset of particles. We are taking 200 particles, trying to find the most correct orientations of these 200 particles against this blob, and then making a reconstruction, taking another 200 particles, different random 200 particles, aligning them and moving like this. And in the end, we are driven by some gradient of the correctness of the structure. And because of this gradient is sending us in the angular space samples from one to other position, it's easier for it to overcome these local probability maximas and climb up to the correct structure. This could be also doable by using the whole dataset, but that would be so computationally expensive that we would wait for a generation of an initial model for weeks or maybe months. The way using of small subsets and many iterations, here we are using around 200 particles per one iteration, and we are using maybe 1,000 iterations of this refinement, makes it quite fast. So these iterations, even if we have 1,000 iterations, we can do it in less than an hour and have a satisfying initial model for further processing. Now, instead of 3D classification, now I will continue with 3D refinement, because some of the things from 3D refinement will apply to 3D classification as well. So what 3D refinement is? 3D refinement is an automated, more or less automated procedure to 3D align our particles against the reference. So we are trying to find the best orientations. These are the best 3 Euler angles that are representing the orientation of our particle projection against the model, and plus applying the shifts. This is a quite time-consuming thing, because you have to sample the whole space, angular space, find all the possible positions of your particles or projections of your particles. In the maximum likelihood version, you are assigning probabilities how well this orientation of the particle is describing the model. And then iteratively, you can take the most probable or integrating the probabilities and weighting the projections and back projecting these to the measured data to get a better reference. And using this better reference, because the better reference has more high frequency information, you can align your particles even better and iteratively going to some convergence. Of course, 3D refinement also has to start with a very generously low-pass filtered initial model to avoid model bias. And plus, there is another thing that's trying to avoid us of biasing our resolution. It's called a gold standard refinement. This gold standard refinement relies on splitting our measured data, all our particles, into two sets, two halves. And into these two halves, we are randomly selecting our particles, and that all the particles are only in one or in the other half, but not there is no particle shared in between the halves. And now what we can do is doing two refinement steps in parallel. We are doing a refinement with half one, converging to some, for us, true structure. And then we are also making a refinement with half two, converging to some extent to a true structure, true model that's representing our data. And what we can do by the end, we can compare these two models, and if these two models are good and they correlate well, they are representing the same, then we can be sure that our model is truly representing our measured data. This is done by so-called Fourier share correlation, so it's done in the Fourier space, and we are doing this gradually over all the refinement. So we are not doing the refinement and then measuring only at the last step, but in every step where we aligned our particles, reconstructing the half one volume, half two volumes, we are comparing how good these volumes correlate. We are estimating the resolution of these volumes, estimation using the FSC correlation between these volumes, and then low-pass filtering these volumes to that certain resolution is our next reference going to the next iteration. We are continuing then until there is no change in the resolution or there are no significant changes in our orientation so that they cannot improve more resolutions. There is something that's good to know, that for our 3D refinement, we can do global and local searches. Both of these searches are important because for global searches, you can think about the sphere that we set up a uniform angular sampling at a certain sampling rate, for example, this 30 degrees, and we have a uniform angular sampling, and every single particle we are checking in this angular samples how well they are representing our model. Now, this can be done till some point where the amount of angular samples are too high. So if we start with some 30 degrees angular sampling, then we get a certain amount of samples that we need to test. But if we go down gradually to 1.8 degree sampling rate, we have so many sampling points that we would not fit either into the memory of our computer, or it would take ages to test all these global orientations. However, we need to do these global orientations because otherwise we can stuck in this called local minima or local maximum of the probability. And that's why what we are doing is in between the iterations, we are not using any of the priors from the previous iterations. So if we find our particle that some Euler angles were the best fit for this particle in iteration 1, in iteration 2, we are not continuing from these known angles, but we are restarting for a global search. So we are discarding this known information, not to stuck in some local minimum. In local searches, however, we take from the last iteration the known Euler angles, And what we are doing is just searching a narrow angular range using the defined sampling rate. This will give us a lot smaller amount of sampling points. But if we would do it from the beginning, it might happen that we would stuck in a local minimum. Using this local search, we need a kind of find when to switch from global searches to local searches. This is usually well defined in the software. And these local searches then can go to very fine sampling rates, which are needed to high resolution reconstructions. So the flow of the 3D model refinement, this is what we already talked about, that we have some initial model in whatever way we have generated it. We have projections of this initial model in different orientations. So we rotate our initial model by the sampling points and the Euler angles defined by the sampling points into different orientations and make a 2D projection of it. And then look that if our particle matches better the first, the second, or the other projection. This is called the projection matching. So this way we will find with what probability this particle number 1 matches the projection A or the projection B or the C, and then we integrate all the probabilities or sum all the probabilities and weight this particle with these orientations to produce a new initial model for the next iteration, which will be again reprojected in different orientations depending on the sampling rate. This is how it looks in reality. This is a nice protein complex of tribolium castaneum hexamerine, it's a red bee flower storage protein. And we start with a very generally low-pass filtered model, which was generated by stochastic gradient descent, yet it was even further low-pass filtered not to introduce any model bias. And we see that even the first iterations are kind of worsening how this looks like, but after a few iterations, iteration 5, 8, and so on, this structure is getting more and more detail rich film. That means that it gets higher and higher resolution. These are the top views, these are the side views. So we can see also from the sides that we get from a very blobby structure to a very nice high resolution structure where we can see the chains of the polypeptides. This is just to show again how the process itself looks like during the iterations. In every single iteration, we are doing the Fourier correlation in between the halves. Then for the next step, we are low-pass filtering the reference according to how well the two halves correlated. And gradually, we are getting better, and better FSC curves. At some point, we are stuck. So these FSC curves are not improving anymore. The reason for that is that we are undersampling our space, our angular space. So there we need to switch for more fine angular sampling, and then we can improve the resolution until to some moment where there is no improvement at all. And this is what we can see that for the first 10, 11 iterations, here we have this 11th iteration, see, we have a sampling rate of the Hilapix order 3, which is a sampling rate of 7.5 degrees. And then we stepwise increased it to 4 because we know that the Hilapix features that only you can go stepwise. So that's the half of the sampling rate. And then for iteration 16, we again change the sampling rate to 1.75 until we find that with this sampling rate of 0.9, we are not leading to any better structures. So we stated as our structure is converged to the best resolution we can achieve. Also, we are not using during the refinement. So the refinement procedure is usually clever enough that if we are starting to align a structure that has a 9 angstrom resolution, then we really don't need all the data till the Nyquist. So internally, it takes the particle, it downsamples the 256 box size particle to 80 something, 82 pixel box size. So it speeds up the alignment process itself. and don't waste the time. And when it finds that we are getting to some resolution where we need a larger box not to be affected by the Nyquist, it downsamples only to a lower amount of sampling. Here our box size, the original box size of the images was 256. We can see that till the end of the refinement process, it never needed the never hit the Nyquist, therefore it never needed the full box size for the refinement. These two charts are showing that we are not monitoring only one thing, that's the resolution, but we are also monitoring how well our angle accuracies are improving. So how there are changes in between the correct angles. So if we state that in this iteration, this was the correct angle for our particle, and in the next iteration it will be a totally different angle, then we know that our angular accuracy in between the iterations is not good enough. And we need to improve it over the iterations. And then we found that by these later stages, 18 to 20 iterations, we are not anymore moving or rotating our particles. They are more or less stacking in the same orientation, and they are not improving the resolution. So this is also one of the criterion how to find that our refinement ended or converged. Now, as I told, I swapped the 3D classification and 3D refinement. 3D classification is a classification that's, again, reference-based, as the 3D refinement was. We are, again, starting with a very low-pass filter difference. We can do 3D refinement before or after refinement. It depends on our data set, and sometimes one or sometimes the other works better. I will explain why we can do it sometimes after the refinement. The classification usually is more sensitive than 2D classification because you can sort out particles that averages well in 2D, but they are not giving information for the 3D reconstruction enough. We again need to do either an orientational search and classification. In this case, we are doing something similar than in 3D refinement, that we are finding the correct rod tilt C angle and shift X and shift Y of the projection of the particle. Plus, we try to classify our particle into one of the classes. It's user defined how many classes we want to have. If there are 5 classes, it will do the angular sampling of the particle and try to fit it to every of the 5 classes and find where it fits the most. Also, a big difference in this 3D classification, if we compare it with 3D refinement, is that we don't have here any 2 halves. We are always working with all the particles because we want to classify all the particles. Now, to speed up the classification, what we can do is to do just classification. So not to do alignment, because sometimes what we have is that we already find the most proper angles of our particles in a previous 3D refinement, and we can use these priors of the orientations and the shifts for the classification. So we'll tell the classification that don't move the particles anymore, they are at the correct place, correct orientation, only move the particles in between the classes. This is a very fast classification and usually works well. It's also supported by the thing that previously our angles and shifts were found using a gold standard approach, which works quite nicely. However, in 3D classification for the orientational searches and this, we cannot use the gold standard approach because we cannot split our particles into halves. Also, what we can do is to tell that we want to do classification and we allow you to do a little bit of local searches. This is again when we need to already know some priors of the Euler angles and the shifts. And 2 other important things, either 3D classification during the process is gradually during the iterations including more and more high frequency information, which is somehow controlled by the regularization factor itself. So the higher the regularization factor is, the higher high frequency information is included in the reference. But it's also affected by estimated resolution of the classes. which is not an FSC based resolution because we don't have halves. So this is a different way how to estimate resolution from the signal to noise ratio, which is not assumed as a gold standard resolution. So to see how Fourier classification works, again, we have our nice complex where at iteration 0, we start a generously low-pass filtered two classes, and then we classify our particle in between these two classes, and we end up at iteration 25 with one class that the class 1, you can see it features more high resolution information because these are more bumpy, these electron densities, whereas the class 2 has more blurry reconstruction. That means that there are less features. We can see it from the top or from the side. For both of these, we can see that class 1 outperforms class 2, and then we can, of course, follow with class 1 and doing another round of 3D refinement. This is just to show how if you monitor the 3D classification, then you need to be aware that many times there are exchanges of the particles in between the classes, and only after certain iterations the classes converge to an extent that there are not any more changes between the classes. This is only for two classes. You can do 3D classifications for many, even for 10 classes. Only thing that you need to be aware of to have enough particles to be able to reconstruct 3D volume from it. So usually you need for a 3D class at least thousands of particles. Now, I haven't covered all the things from the SPA because there are many other techniques that are very useful and interesting, like localized reconstruction, and then there are modern methods for correcting the images as CTF refinement, third order, fourth order aberration correction. These are today out of the scope of this lecture. They will be covered in the advanced cryo-electron microscopy methods. So you are very welcome to follow in the next semester on these lectures. Yet I want to conclude our SPA lecture with some limitations of the SPA. The first limitation is, and this is very important to know because many people are struggling by setting the correct parameters, trying to find the best way how to reconstruct particles by computational approaches, but no computational approach can replace the perfect sample. So if you have a bad sample or a badly collected micrographs, then no computational process can save your data. So the aim is at first to have the perfect sample, then the processing itself. SPA is limited by preferred orientation of the particles. We assumed at the very beginning of our lecture that we have an evenly randomly distributed orientations, all possible orientations of the particles in the ice. This is rarely the case. This can be sometimes overcome by the symmetry of the particles when the particles have a certain symmetry. Yet also this preferred orientation is sometimes a wet lab work when you need to find a proper sample preparation which will avoid to have these preferred sample orientations. SPA works the best if the heterogeneity of your particle is low, so the particles are uniform. You have the particles in all possible orientations and the particles are always representing the same thing. Of course, you can 2D, 3D classify your particles on arrays of classifications, but if your particle is very flexible, then these approaches are not leading to satisfying results. There are approaches how to reconstruct flexible complexes. Again, these are out of the scope of this lecture. And of course, either SPA is the way to go for the small complexes or small particles. The particle size still limits us, so I would say the smallest particle that you can analyze with SPA is the particle that you can see on the micrographs. If you don't see the particles on your micrographs, then you can hardly box them. And if you box them, if they are not there, then you are boxing noise. The last thing, some computational demand. Nowadays, all the software is optimized for CPU or graphic cards, GPU accelerators. I would say that it's even the Cryo-EM is even doable on some personal workstations to a certain extent if you have a reasonable box sizes. The larger the box, the more demand on the random access memory or the random access memory on the GPU, because by increasing the box size, the usage of RAM increases by the cube of the box size. And of course, all of us know that a Cryo-EM is heavily using disk storage because all our data sets are in terabytes. So this is also something that people need to be aware of. And this is all for today. I hope you enjoyed this presentation, this lecture. We will meet tomorrow with the tomographical approaches. Thank you for your attention, and if there are any questions, please ask.